what do theories say about our peripheral visual experience? So some theory says that our impression of seeing color all the way to the periphery is illusory. And they suggest that there are multiple possible mechanisms underlying this illusion. And one of the hypotheses is that there are eye movements happening all the time, which is unconscious, and we cannot, consciously sort of, detect when and where we are moving our eyes, and that explains this, phenomenal illusion or expectation. Like, we expect that the skies are blue, and therefore, we always feel like skies are blue, but we are not seeing the blueness at the periphery. Or the memory, like in my room, I know that beds are here, which is green, and so here it's a white wall, and I have already developed this kind of expectation, a memory through my interaction with the room. So even though I don't see the color here and there, I actually unconsciously infer that they are this color, and that sort of paints my belief that I'm seeing the colorful room all the time. That's this kind of the combination of many of these types of the mechanism explain this impression of the peripheral illusion. So in this video, let's examine the plausibility of these explanations. First, I want you to hear what the Daniel Dennett, who is one of the most influential philosophers, say about this in this Mindscape podcast by Sean Carroll.
Yeah, well, it calls up the reliability or the usefulness of introspection generally, right? I mean, introspection is where we get a lot of these ideas of our experiences. Should we be generally skeptical of introspection? We learn something from it, certainly.
We learn something from it, but yes, we should be skeptical. First of all, let's start small and build up. I love to point out to my students and others all the ways in which their consciousness isn't the way they think it is. For instance, it seems that our color vision goes right way out to the edge of our vision. It doesn't. It seems that we have high resolution vision out to the side. We don't. I love to point out that lots of things that are surprising, I can demonstrate to them. I think, whoa, who knew that? Well, you didn't, did you? So forget about the so-called incorrigibility of first-person acquaintance. That's just a mistake. That doesn't mean that we're not reliable informants to ourselves and others about many features. But forget about this Cartesian idea that on the inside, we are the masters of what's going on.
So you're saying that even when we experience the outside world, there's a lot of stitching and jiggery-pokery that comes together to give us this image we have. So why shouldn't the same thing be true about our introspection?
Well, no, I think that, yes, I think that we have very clear cases where people misintrospect, if you like. And that raises the possibility, which I think every theorist is really sort of honor bound to take seriously.
Okay, so that's good enough. So then Daniel Dennett is quite skeptical about the intuition or introspection, as he says, all right? Then let's go. So he and his colleague has been quite explicit that our conscious experience is sparser or different from what we think. And wait a sec. Yeah, so Dennett and his colleague has been quite explicit and skeptical about our consciousness from an introspective point of view. And he and colleagues claim such as, we still see far less than we think we do. So I want you to, verify this kind of statement by yourself. Did you actually thought that, the color has to be actually, very close to the phobia to identify the color? Or was it like this, where you actually thought that, card would be, possible to see its color even here, but it turned out that you cannot do that. Which one was your, experience? So the prediction from, Dennett's side is coming from some kind of physiological facts like this. As we went through last week, that this is the cone distribution in terms of density as a function of eccentricity, right? And within 10 degree, which is roughly on as I depicted on the display, the cone density falls off really quickly. And if these cones are supposed to be responsible for the conscious experience of the color, then as Dennett says that our vision should not be as color vivid as to the periphery, all the way to the periphery, and also we should not see clear vision in the peripheral areas. So their hypothesis or explanation is that we actually do not see color in the periphery because of the lower density of cones at the periphery. Okay, and somehow we feel color in the periphery. So the explanation they invoke is the following. One of the reasons, for example, is the unconscious eye movements. So at the phobia, we always see, very clearly. That's what they, don't deny, right? However, the hypothesis is that we feel like we see color in the periphery, like almost like a light in the refrigerator. So this metaphor is very famous. Oh, if you open up, a refrigerator, inside the refrigerator, there's always light, right? So you can always see, what's inside. And if you're, if you don't think about it very carefully, then you might think that, refrigerator inside is always bright, but it's not the case. When you open refrigerator, there's a, mechanism that makes, inside lighter because of this kind of, circuit, right? So analogy of this thing is that when you look at the periphery or when you attend to the periphery, then there's always a color, but once you move your eyes to somewhere else, then you don't see the color. And this is accompanied with another kind of mechanism, which is that you are not aware that we are moving your eyes to see the peripheral color at the phobia, and that's their explanation. And this is, to some extent, intuitively makes sense, ironically, based on the following kind of, puzzles of the eye movements and the consciousness. One of the facts that you probably don't know is that you move your eyes roughly 3 times per second. And if you imagine that, moving your eyes, like, right, you can try it right now, makes the vision, kind of, really hazy and also, all the way all over the place, then we should actually notice this alone, right? But we don't notice. So there must be some kind of mechanism that makes our eye movements unconscious. And their idea is that we are really normally unaware of the eye movements. But this is not the same thing that you can become aware when your eye movements happen if you pay attention to it. So if you pay attention to your eye movements, then you know that, oh, yes, I am moving my eyes, right? But still, the more interesting thing is that during eye movements, you cannot actually see things clearly. So let's go with this eye movements and the conscious vision demonstration. First, one way to do it is a face to your friend or record your face with the videos. But the videos are not that great, and unless it's high resolution, high temporal resolution. And then you move your eyes quickly. And then can you see the movements of the eyes of the other person or in the videos? So if I do it like this, I don't know whether you can see it with these small videos, but potentially you might be able to see my eye movements. Okay, so if this is possible, then that means that you have a sensitivity to see the motion of this small black and white thing with your eyes. Okay, that's one thing. But then go in front of the mirror and then look at your own left eye. All right. In my case, I can actually do it on myself by enlarging it like this. And then I'm now looking at the left eye and then look at my right eye, left eye, right eye, left eye, right eye, left, right. And then something like that, if you try it, can you actually see your own eye movements? I predict that if you try that, you probably won't be able to see your own eye movements. I can kind of see it right now because there is a delay, okay? But still, it's very difficult to see. But if I see other people's eye movement, I should be able to see it really clearly. And why is that? That's a question. And it's called a saccadic suppression of the conscious vision. So this is one particular experiment that showed this, saccadic suppression very beautifully. So here in this experiment, the experimenter asked the people to look at this location first, and then made an eye movement to here, saccadic target. And then at some very different kind of timing, with respect to the saccade, they flashed some kind of stimulus here. Okay, and then ask the people whether they notice any kind of flash over there or not. And then it turns out that the performance of the detection became quite impaired around the time of the saccade. So if you make an eye movement around here 0, okay, so let's say if this is a time course of the eye movement here, and then at 0 the eye moved like this. So this is a kind of time course of the saccade. And then the proportion of the correct trials, like detection of this flash of the light, becomes at chance 25%. This is a chance performance around here, completely at chance around 20 to 30 milliseconds after the onset of the eye movement. So while you are moving eyes, you actually cannot see this kind of big stimulus near the fovea. And interestingly, it also happens that your visual impairment starts to happen even before, like 50 milliseconds before saccade, and also after 75 milliseconds after eye movements. So during this eye movement period, your vision becomes gradually worse, and then becomes completely blind, and then comes back gradually. But we don't notice that. So something happening in the brain is editing this kind of blacking out and then recovering of the visual sensation over the time every 3 seconds. But we are completely unaware of that, and that kind of lends a support to the Dennett's type argument that we are actually making a saccade to periphery, and you are not really aware of that usually because every time when you are making a saccade, that there is a blank of the vision, and that helps us not to notice this kind of artifacts or illusion. All right. So to cope with this kind of criticism or hypothetical scenario, what we can do? If you really believe that your color experience at the fovea, outside of fovea, is actually true, right? One way is to directly measure eye movements, and then I can make sure that without moving our eyes, I'm still seeing the color that is not expected or memorized. But this can be tedious. So one way to do it, to avoid this kind of eye movement measurement, is to present a stimulus for a brief duration, like less than 200 milliseconds, and then present the color stimuli at a random timing and random position. And then we can exclude the possibility of expectation and memory and those eye movements, right? And that's exactly the experiment that my postdoc Ariel did recently. And even if under this kind of situation, if you try to make a saccade, then as I said, before starting eye movement, it starts to degrade eye movement, the vision, and then by the time when you arrive there, there is a blank of vision. So in the end, if you try to move your eyes during this brief period of the time, then your color experience should be impaired, in fact. So what Ariel did exactly is the following experiment. So after the 500 milliseconds of the fixation period, he would show 2 patches of the color at a different size or the same size at the fovea and the periphery, and then ask the similarity of the color between the two. And then go to the next trial. And every trial is a random position and a random color. So what happens? So because of the locations are random and durations are short, eye movement should be blurring the vision. And that's why we can exclude the possible contamination of the expectation and the memory. So here's the demonstration of the video task. So here you see 2 colors, right? Red and purple, and then green and blue. And then you can report the dissimilarity level from 0 to 7. That's green and green, nearby fovea and periphery. And then I would say that dissimilarity is 0. And then blue and green, dissimilarity is maybe 3 or something like that. And then red and purple again, red and pink. So that's roughly dissimilarity of 2 or 3 or something like that. And then this is now repeating, but in the real experiment, it's all randomized. Okay, so that's how the real task works. So what he found using this different size of stimuli, like the one that you saw, small one at the fovea, 0.1 degree visual angle, and 0.45 degree visual angle at the periphery. Then initially, he looked at the similarity structure between the foveal 2 colors. That should be visible in terms of color vividly. And then what he found was that indeed, each of this same physical color was rated as highly similar. So like 0 or 1 or something like that. Orange and orange, that was also rated similar. And the green, that's also similar. So this all these diagonal entry corresponds to the physically the identical stimulus presented at the fovea, and then they are all rated as highly similar. That's okay. And then similar colors such as here 3 different shades of the green, right here and here. Then any pairs of the greens were also rated as similar, right? But if it's pairs of the red and the green, then they are very, very dissimilar. Whereas the red and pink, then that's more similar. So this is only, this kind of, very detailed structural comparison is possible when you see things consciously, okay? Next, what he did was to construct the same kind of data, but now comparing between the foveal to peripheral color, which is this part of the figure, or periphery to peripheral color here, right? And then, as you can see, almost immediately that structure of the color similarity is the same, basically, essentially the same between the center and the periphery. And this is a strong evidence to say that without any expectation or memory effects, because it's all randomly presented, we can clearly see the color and we report its similarity in a highly consistent and reliable manner. So in some theories suggest that we overestimate our experience of the peripheral vision because of our movements, memory, and expectation. However, After removing these confounds, using a brief random presentation, we still see color reliably. So then you might ask, why? How is it possible? I understand, I can trust my, phenomenology maybe, but if there's no color cones at the periphery, then this cannot be the case. How is it possible? So that's the question we'll address in the next video.